Cool. Well, welcome today, folks, to my talk, Better Understanding Through Bytecode. I gave this talk previously at JBCN, but the video for it didn't get released, so I'm excited to give it to you all again today, just so we can share it more broadly and make sure this recording goes somewhere. So let's dig in. A lot of times when we run into problems in software, we try to figure them out by abstracting things away, right? I'm an architect, right? This sort of drawing is my bread and butter. Like this is, what I do. But I think that sometimes there are certain types of problems in certain areas where digging the other direction is really valuable. Digging down into the details is going to tell us things. Now, this doesn't work for every problem in every situation, but when it does, it can really yield us different insights than the sorts of insights that we get when we abstract away by going down a layer. So that's what we're going to do today, specifically on the Java platform and looking at bytecode and what this sort of bytecode level of the system can tell us about how our software works and what happens. So first off, because this isn't something that you necessarily do every day as a Java developer, we're going to get a few tools to be able to start digging around in these areas. We're going to talk about how the JVM actually runs bytecode a little bit, and we're going to get tools to look at the bytecode that comes out of our stuff, out of our code. And then we're going to use that and apply it to three very specific examples and see what we can learn about them by looking at the bytecode layer of the code and see what's different from our Java code, see what's unexpected, see what it tells us about what's going on. Now, if there's anything that I want folks to take away from this talk, even if you don't remember the bytecode specifics, even if you don't remember the examples, the real big takeaway here is that you can understand the layer below where your comfort zone is. Whatever that comfort zone is, there's something below you that you probably don't dig into very often. You can get there, and it's useful to look at it even if you don't understand all of it right now. Like, I'm not going to explain every single bit of bytecode that's going to flash across the screen while we're doing this, but you'll see how having a few nuggets of understanding, a few sort of toeholds into it, is enough for you to get something useful and concrete, and you can build your understanding from there. This applies to almost everything I've seen in technology. So we're going to learn to not be afraid. We're going to dig in, and we're going to use the pieces that we do know to try to understand the system better. All right, so where we're going to start off from is a little bit of a high level of how the JVM actually executes things. And then we're going to look deeper at the actual bytecode and what that means. So at a very, very high level, the JVM works by, you take Java source code, you compile it into a class file. The JVM actually doesn't know anything about Java, the language, or whatever your source language is. It works on class files. The majority of those class files is what's called bytecode. This is a sort of intermediate representation of all the methods and all the information that you've put in your code. So when the JVM runs, it loads your class, maybe does some amount of transformation on it, and then at first an interpreter runs through and executes that bytecode. Now, eventually, if a method's being executed enough, it might get JIT compiled, which is the JVM turning it into really fast machine code so that it just screams and goes super fast. We're not going to say anything else about that today. We're living entirely in interpreted land where we're dealing with the bytecode as it kind of comes out of the class file natively. Now, we're not going to look at all of the bytecodes that are there today, but I can recommend a talk by Ben Evans, former Relic, who he gave a more thorough presentation that was just about all of the different types of bytecode and how they operate and how to do that. So that is well worth your time if you're interested, if this sort of talk tantalizes you and you want to go deeper. There's also a book I could recommend. There's an entire chapter in The Well-Grounded Java Developer, which I wrote with Ben and our friend Martin, that deals with bytecode again in a more thorough presentation. But we're going to learn just enough of it today for us to be able to understand what's going on and start poking around. All right, so at a high level, JVM loads class files, executes bytecode. Well, how does it actually do that execution though? Like there's got to be more detail to it. And the detail that I want to talk about today, sort of drill in on, is that there are two stacks or two types of stacks that we need to think about in code execution in the JVM. The first is actually pretty common and pretty familiar to us as Java developers. That's the call stack. You've got every thread in your Java application is going to have a set of methods that it's called through and a stack of things that's there, and each of those spots, you know, is represented. Oftentimes, when we throw an exception, is when we see our stack traces directly, or when we're debugging, you can see those as well. Each of these method calls then is what's we call a call frame, and so this is sort of the representation of one particular call of a method. And it has some important pieces that we want to look at in how the JVM actually executes. First off, it knows who it is. So it knows where it came from, it knows its parent, and then if it calls another method, it knows what methods came after it, understands the stack that it's part of. It also has what we call slots for local variables and arguments. And so this is sort of like internal scratch space where this particular call frame can do its work. Each call frame, even if the same method gets called again, it has its own independent set of slots. This is completely local to just the method. It's the arguments and locals that are here. And also local to the frame, to this single frame, it has an evaluation stack. And this stack is where the JVM actually does its computation. So all of its computation, all the interesting machinery takes place using this evaluation stack, which is local to this frame. Now, if you've done assembly or things where, you know, you have registers and you have all this stuff that's really specific to the CPU, the JVM is not like that. It's a very simplified sort of evaluation model. It's a stack machine, and it just works with that stack. And that makes it really easy for it to do that JIT compilation and optimization later on, because the bytecodes are actually really generic. They're very, very simple, and they're designed so that they can be optimized later. All right, so that's a little bit of sort of the frame of where we're going to look at this execution. So let's get into the bytecode. Let's try and learn how a few of the primitives work so that we can start looking at those examples and seeing how they work. So the code that we're going to take in most of these cases is going to be really pretty simple code, largely because bytecode gets really long. One thing you can say about it is it's not really written for humans to read as a primary thing, and it can be very verbose. It's often pretty simple, but just long. So for our purposes, we're going to take some pretty simple methods. The first one that we're going to take, we're going to have a class with a instance method on it that takes two numbers and adds them together. Now, if we compile this into a class file, we can then use a program that comes with the JDK called JavaP to sort of poke around and look into that class file and find various information in it. The particular flag that we're interested in is the -C flag. So when we pass -C, it's going to emit all of the bytecode as code from the class file that it's reading. If you don't give it that, it'll give you like information about the classes. It might give some method names. You know, there's a more stripped down view, but we're really interested in what all of those, all of the actual instructions are that we're looking for. Now, this brings us to my first trick when we're dealing with bytecode. Because it's often so voluminous, look for what you recognize and ignore the rest of it. Like, there's going to be stuff all over the place that is, you know, maybe a little baffling, maybe long, maybe not, you know, maybe generated by the compiler. We'll see some of that later, where there are pieces that are only tangentially related, it seems like, to what you wrote. So find the hook where you can recognize what the thing is and move from there. So for us, the hook that we recognize is down there towards the bottom is our add method. There's our signature for the method that we had written And right below that, it will have the code. So let's dig in and let's look at what the bytecode for this actually looks like. So over on the right, this is the representation of our add method as bytecode. And what we're going to do is we're going to step through and introduce each of these instructions and step the machine of how it works with our evaluation stack and how it works with those slots in our frame. So we're going to call the method with 10 and 32 as our two numbers. So we can see at first, when we come into the method, our slots are already partially occupied. So we have slot 0 when you're calling a method that's a instance method. Slot 0 is always going to be the object reference. It points to this, the instance of the object that we're talking about. And then our various arguments flow in sort of parameter order. So slot 1 is going to be the 10 that we're passing in. Slot 2 is going to have our 32. All right, so we start executing the method. And the first thing that it does is an iLoad1. So there's a variety of different load instructions. The I prefix means that it's working with a primitive integer. There's a prefix for each of the major primitive types. We'll see a couple of other ones as we go through. And the 1, it's so common that people access slot number 1 that there's an entire bytecode that's just devoted to that. You can actually do loads and then pass it a second byte, which tells it what slot to go get, but that would be twice as many bytes to represent the instruction. And so they've compressed the very, very common ones with this _1, _2, _0 sort of nomenclature. All right, so when we do iLoad1, what that does is that reads from the slot, number 1, and it pushes it onto our evaluation stack. So now our evaluation stack has a 10 sitting on top of it. Well, load 2, as you would expect from the description of the load 1, it's going to look at slot number 2 and it's going to push the 32 onto our stack. So we now have both of the numbers that we passed in our evaluation stack. Our next command does an iadd. Iadd will pop the top 2 values off of the stack, add them together, and push the result onto the stack. So we end up with 42 sitting on the stack. If you ever have used calculators that do like reverse Polish notation, this is exactly the same sort of setup. And then our last command, last bytecode here is iReturn. That says return the integer value that's sitting on the top of the stack. And that will go to whatever the parent calling frame is for that value to do. So there you have it. We've broken down our first method. We've looked at the bytecode and we've stepped through each thing that it does. We've seen how it loads and stores, a little bit of arithmetic, a little bit of returning stuff. All right, so what's next? Next up, let's look at a little bit more complicated example. So we're going to have a local variable. We're going to put the string hi into it. And this is going to reveal a couple of different things that are worth us knowing. So the bytecode for this is actually only three bytecodes long. So we've got LDC number 2, and the decompiler has very helpfully shown us in a comment after that that's the string hi. So number 2 represents a constant, and there's a variety of different constants that are in our class files, and we'll take a look at how those work in a moment. But LDC will take and load a constant from the constant pool and put that onto our evaluation stack. So we can see here, LDC2 has resulted in the object hi, the string that represents that, sitting on our evaluation stack. All right, our next instruction is a store 1. So a, like we had I previously when we were dealing with integers, a is an address, so an object reference, and store is the opposite of load. So it will pop whatever was on the stack and it will put it into a particular slot. So slot number 1 for us represents that local variable that we were wanting to assign into. And so we're going to pop our string and assign it into that spot. Last but not least, our method was void, so it just is going to have a return at the end. There's no type on it because we don't really care. We're just exiting the method rather than actually returning a value to another caller. So That's store and loading constants. Now the constant pool is where those constants live. And if we pass Java P a -v, it will spit out the constant pool. And so in this particular case, if we had looked at it, we would see number 2 is defined in there. It's a string that references some UTF data. I think that UTF data can be used by things other than strings. So that's why it's broken apart like that. Number 13 then is the actual UTF characters for H and I to represent that. There's a lot of interesting stuff in the constant pool. Actually, apart from looking at the bytecodes for your individual methods, the constant pool is one of the most interesting parts of breaking a class file down to kind of see what's around in it. And we'll see another couple of parts as we go a little further on. All right, so one more set of example bytecodes actually, and then we're going to be ready to start tearing into some of those examples and putting these tools to work. So Java is an object-oriented language, so creating new objects is obviously critical to understanding how things work. So we're going to have this method. It's going to create a new object. It's going to store it into a local variable. And we can already see a couple of things that look familiar, but a little different. So these are constants, number 2 and number 1, but rather than being string constants, these are constants that reference classes or methods. And that is how, calls between methods and constructing classes, those get referred to by those constants. We'll see those in action in a moment. We can also see other parts of this that are exactly like what we had done before. We've got our a_1 to store into our local variable. It's a void method that we're not even returning the object from, just to keep it simple. And so we end up with just a return. So let's step through this though, because there's a little bit of flavor to how it creates the object that's worth understanding and some patterns there. So the first bytecode that we encounter is the new bytecode that will allocate an object of the class that the constant is it's passed. So it's passed number 2, that represents the object class in this particular class file. So this will allocate the memory on the heap for that object. Now, you need to understand at this point, the constructor has not run. This is not actually a fully ready object. This is just allocated. It's just been the barest amount of creation for it. Now, interestingly, for reasons that we'll see in just a moment, we call dupe. So now we have 2 references to our object sitting on our evaluation stack. The reason will become clear in just a moment after we do the next line. But first, we need to invoke something. So invoke is the terminology in bytecode for running methods. There's a variety of different invoke flavors. We'll see a couple of them as we go along. In this particular case, invoke special is the bytecode that's used to run the constructor. And in the bytecodes, you'll notice when you write your Java code, you're not writing a name for the constructor method. You just sort of give it the class name. It actually, under the covers, turns it into a method which is named angle brackets init, which is not actually a valid it's not actually a valid name that you can use in Java. So you can't accidentally define a method that's named the same thing that the constructor is. And so this will actually go and run the constructor. Had a question in the chat about why the instruction number goes from 0 to 3. The reason for that is because the constant that it's passing, the number that it needs to pass to after the new bytecode, takes up a couple of bytes itself. So you can have bytecodes. The actual instruction will always be 1 byte, but some of them may be followed by other argument values. And so in this case, the 2 bytes that follow new are for representing a location in the constant pool for it to do. So that's why those are not 0 and then 1. And you'll see that in a variety of other spots where they'll always be increasing, but they won't always be exactly sequential. All right, so once we've invoked a method, you'll notice that the evaluation stack has popped the reference to the object that it's doing that invocation against. And so this makes sense of why we needed to dupe that, that reference, because if we'd left only the original one that had come from our new, then when we invoked the constructor, we don't have a handle to the object anymore and it's gone. not very useful. So we duped it so that we have an extra copy there that can get shoved into a local variable. And in this case, because we were just simple in our method, we're just going to return without doing anything more interesting with it. All right. Believe it or not, we now know enough bytecode for us to go look at an interesting example and learn a little bit about how the JVM works at a deeper level. And this particular example that we're going to pick up is the classic one of lost concurrent updates. So we're going to work with a very basic class, an account class. So you can imagine that this represents an account at a bank. You have a balance in it, and then this method has a transfer method. You give it an amount that you want to transfer to another account. It checks whether you have enough, and then it does the pluses and minuses for the various things. If you think that this looks like a good way to implement this or good solid banking code, I would like to ask you to not work at my bank. Because as anyone who's worked with Java for any amount of time knows, this is rife with problems once we get into any sort of concurrent system. And we can actually demonstrate this with as little as 2 threads. So if we run a little script here that will create an account with 10,000 in it, create another account with 0, run until the account drains all of its stuff and try to transfer one by one, and run that from only 2 threads. Like just 2 threads. You'd think maybe 2 is going to be fine. It's not going to get into too much trouble. You're going to get a completely different amount every single time that you transfer. This is classic sort of lost update that happens during concurrent operation. And at the high level picture, you know, we can look at it and we understand that, like, oh, the 2 threads are kind of contending over these values. They're at different points in their execution, and stuff sort of gets mixed up. But I think it's actually really powerful if we break this down to the bytecode, because then we can really see precisely what's happening and how the ordering of things comes into play. We're also going to learn a couple more interesting bytecodes in doing this, but they look a lot like the ones that we've already seen. So here is the entire implementation in bytecode of the transfer method. This is about the largest single thing that we're going to look at all in one go. And as you can see, there's a lot of repetitive stuff in here. One of the big repetitions that we keep seeing is get field number 2 and put field. So get field and put field, as you might expect, are bytecodes that operate on an object. They get the value of a field and put it onto the evaluation stack, or they pop what's on the evaluation stack and put it into that field on the Java object that's sitting there. And so we can see, as you would expect from the code, this is accessing that balance field repeatedly between the 2 objects that we're dealing with. We also see here our first instance of some flow control. So we haven't seen any ifs or whiles. Well, whiles and loops don't actually show up in bytecode. Those get turned into just go-tos, but branching instructions do exist. And we can see those represented here. So this is what our check for our do you have enough in the balance turns into, and then the if lcompare, that does the comparison, and then if less than 29, that says if we don't pass, then go jump to 29. So this is essentially like a go-to when we don't meet the condition. So we'll walk through the execution of this, but that's sort of where the if that was guarding whether we do the balance transfer or not actually shows up. All right, so let's step our machine through. So our starting position that we have, this is, because this is a instance method on the account, this is in slot 0. Our first value is 100. It's a long, so it's actually going to take up 2 slots. It takes up 1 and 2. And then slot number 3 is a reference to the other account that we're going to be pushing things into. So our first step, we load to put this onto the stack, and then we do a get field to get the value from its balance. So that puts 10,000 from our original starting balance onto the stack. We're then going to iload 1. So this is the amount that we're wanting to transfer that we passed in as a local argument. We're going to put that onto the stack as well. And then we're going to compare them. Now this lcompare, I always forget the direction. It's like -0 or 1 is the protocol. It plays well with the if instructions. So the lcompare or icompare for the various different flavors of numerics work correctly so that then you can say, hey, do the comparison. If it's less than, go jump. In our case, 100 is not less than 10,000, or it is less than 10,000, so we're fine to continue, so we don't want to skip. So we're going to blaze down into the inside of the if condition. So we're going to load up a couple of this pointers to our object. The first thing that we're going to do from it is we're going to get the field again. So we've gone and retrieved our balance off of the object yet again, and then we're going to push our amount that we're wanting to do to subtract onto the stack, and then we do a long subtraction to sort of get what the value is, the decrease. So this is the minus equal line, effectively, is what we're executing at this point to sort of deduct from the account. We put the result of that back onto the field. That consumes the this pointer that we had sitting on the stack and the value for the field. And so now we're back to an empty stack. We're going to load the other account up like before, because we're going to get the field and put the field. It's going to dupe it to begin with. We grab the value, we do the addition instead of the subtraction to get its new value, and then we put the field back onto the object. So you can see how this maps very much just step by step to the things that we were doing over in our Java code. So, but why does this tell us more? Why do we get to understand more by doing this at the bytecode level? Well, the important thing to remember is like each of our threads is executing its own steps through bytecode, talking to the same objects in this case. And which of these fields, like which of these instructions can interleave? Where can each of them be? Anywhere. There's no synchronization between these two sites. You could be at any of these possible locations. And as you remember, like we read back and forth the different values on those fields multiple times into our local evaluation stack. So each of those threads, because they have a local evaluation stack of their own, there's like effectively a hidden location. There's a hidden spot where those intermediate values go. So when we've talked about it in Java code, it's like, yeah, they can both be executing, and they have each of the threads kind of knows their value for something. It read it somewhere and then hasn't updated it. Well, now we can see precisely where it is that it read it. It read the value onto the evaluation stack, which is local. And that's where it comes from. This also tells us that because those bytecodes on the different threads interleave, there really is no possible way that you can make this work without applying extra synchronization. Any given line of Java that you have may well have multiple bytecodes. And if it results in multiple bytecodes coming out, you have no control over how those are going to interleave with execution on other threads. So this has taken something where we kind of have, when we talk about it in general, we've got a model that sort of, it makes sense and we can reason about it, but this makes it really precise why we get these sorts of concurrency problems. All right. So that's a fun example from the threading world. Let's talk about recursion, and specifically tail recursion. So a recursive function is a function that calls itself. If you've been practicing your CS stuff, you might have written a factorial function. Here, factorial, we define it by taking taking the number that we want to get the factorial for, calculating the factorial for one less than that, and doing the multiplication. This is very classic, very standard. The problem that you run into is that, if you call it for a big enough value, you're going to get a stack overflow. And that stack overflow, I think, where we've been, we can kind of understand a little better why we end up getting a stack overflow and why that's a problem. Like when we recurse, those stack frames that we were talking about, they have actual storage and size associated with them. They are using a limited resource of space. And so we can't stack an infinite number of frames of execution, or we would run out of memory to be holding them. Every single one of those things that we put onto it is a problem. And, you know, you're going to end up running out of space if you do that. If you have something that sort of keeps going and keeps recursing, then eventually you're going to exhaust the memory that is available to the JVM for it to be able to do that. All right, so a classic way of fixing this is what's called tail recursion. Now, I will say up front, this is not something that Java actually supports. So we're going to look at how it does things, and then how it could be different and how it would look if it was implemented differently. But let's talk about what tail recursion is first and why it would solve our problem. So with tail recursion, the last call in a method that's recursive has to be the recursing call. In our factorial case, this was actually not tail recursive. We call factorial and then we multiply by n. Now, you can always rewrite a recursive method to be tail call ordered. Sometimes it's ugly. It can actually make these really elegant recursive things that you're trying to do not nearly as elegant as they were. But it is always possible to do that transformation and sort of reorder how things are being done. For our purposes, again, because bytecode gets long, we're going to take a simpler tail call sort of function. So we're just going to have a function that purposefully overflows. It just calls itself. So the last thing that it does is just calls itself, incrementing the number as it goes along. Now, as you'd expect, the bytecode for this is pretty simple. We end up loading in 0 when we first are loading from slot 0. This is going to, on its first invocation, be passed 0. We're going to push a 1 onto our evaluation stack, add those together, and then invoke static. So this invokes the same method. The reference to it is in constant number 2 this time. So this is going to invoke ourselves. So this creates another stack frame on top of it. Now, interestingly, we're never going to see this returned, because you never actually end up getting back from this. It's always just going to invoke that other method, and it's going to just stack frames up until the JVM goes, well, too deep, I can't do that, stop, throws a stack overflow exception. So as mentioned, there's really nothing we can do about this in Java to be able to make this work properly. But there is actually a solution in a neighboring language called Kotlin. So Kotlin actually has a keyword that you can apply to a function that's called tailrec. And that says, hey, I know that this is tail recursive. I don't want you to stack overflow when you're doing that. So let's take a look at what it does and how it changes the bytecode to be able to apply that tail recursion. So not too much longer than what we were. We come in and so we start off by doing a load 0 of our argument. So that was the 0 that we initially passed in. We're going to store that into location number 2. The reason that these are in 0 and 2 and that 1 is unoccupied again is because these are longs. So they take 2 of the slots in each of their cases. That probably could have been shown a little better in the diagram. Once we've got that into location number 2, then we load the value back from it. We add 1 by pushing the constant 1 and then doing the add. Then we store that value into that same local that we had done previously. And now, instead of calling the method again, because Kotlin recognized from our keyword that this was tail recursive, it just says go to 2. It moves to the second instruction after we had done that initial load. And this is why it was reloading from that local. And so what it's effectively done is it's turned a stack frame adding sort of method call chain into a loop. And in this case, infinite looping here is better than overflowing. Like this is going to block forever, which is not awesome for real code, but in our terms, we avoided that Stack Overflow exception. And if this were something that were actually a real tail recursive sort of situation that would eventually terminate, it would be a better situation for us that it would be able to do this sort of computation. So we can see how at the bytecode level, something that looked like it was method calls could be rewritten as something that was just a series of go-tos. So our recursive function, if we turn it into something that's tail recursive, that tail recursion can get turned into a loop, and that loop at the bytecode level can just run however it needs to. There's an interesting result from this as well, because like we said, these recursive functions, you can turn recursive functions into tail recursive functions. And if you can always turn something tail recursive into a loop, that means that effectively any recursive function could be re-implemented as a loop. It's just a fancy way of looping with method calls, which is kind of a little mind-breaking. Everybody treats recursion like this computer science black art, but it's just a bunch of go-tos under the cover. All right, so that's a pretty fun example. We're going to step up a level with this last one, and we're going to look at coroutines. So this is, again, a feature that comes in Kotlin, not in Java itself. In the in today's day and age, you may hear a lot of talk about a thing that's coming to the JVM called Loom. Project Loom is going to create virtual threads, which allows us to sort of have computation start and stop across threads without having to spin up a new thread at the OS level for all of these different pieces. It's probably coming in Java 21. There's some preview bits of it that are available, but Kotlin has had something called coroutines, which essentially does a lot of the same stuff, and it's been running on the JVM since at least version 8, that it's been able to do this. So what a coroutine looks like in Kotlin, this is sort of one of the simplest cases of it. So we're going to say global scope and then launch, and we have 3 functions that we're going to call inside of that: first, second, and third. So those functions, what's going to happen when these get executed? That global scope says, I'm launching a coroutine. Please go spin this off somewhere. I don't really care about exactly which threads it executes on. It's going to start, it's going to execute the first function. It's then going to pause. Other stuff might happen. The runtime gets to determine when it starts up and does the next step, running the second function. That then also is going to pause before it goes on to the third. And the way that it knows, the runtime knows, Kotlin finds out that these pauses should happen is because there's a keyword in the language. The keyword is suspend. And what that says is when this function gets executed in a coroutine, you can pause at this point. It sort of indicates where there's some handoff points. This may be a little different from the way that Loom's going to do things. I think it's handling things around like when you do blocking IO. That's also built in with Kotlin stuff where whenever you go to make like an IO call or something, those are also suspend functions. A lot of things in the base library are suspend, and so these coroutines can stop and then start again. All right, so let's see if we can understand how this got implemented on earlier JDKs, which didn't have virtual threads built into them by themselves. So the first bit, we're just going to use the Kotlin compiler, compile that single file that we had. So we had coroutines.kt. Kotlin allows you to have standalone functions, sort of top-level functions, but the JVM actually doesn't allow that. You can only have methods inside of classes, and so it generates wrapper classes for things. So that's actually part of what we're seeing here. That first wrapper, or that first class, the one with $main in it, that's sort of the synthesized class that it makes to wrap that function. But you'll notice that there's another class there. Like our single Kotlin file generated more than one class. So this is already telling us that like something interesting is going on here. Most of the time in Java, you compile a class, you end up with one class. Here we're compiling something and ending up with multiple pieces. All right, so let's go look into that first spot. So if we look around in the class file, we're going to find that we can spot our static public void main. So our main entry point, which it looked a little different in the Kotlin version of it, but this is the equivalent of that main function that we had. And don't worry, we're not going to get down to like the individual machine steps on this one. We're going to take it at a little higher level and just sort of flex our ability to scan for things that we know, find the bits that are familiar. All right, so the first thing, it does a get static of this global scope instance. So you remember that when we launched the coroutine, we said global scope.launch. So this is it going and getting a hold of that global scope that it's going to run the thing against. There's a few intermediate steps, but then we see our object instantiation pattern. Now, if I remember correctly, we didn't say new on an object in that method. We didn't construct an object ourselves directly, but there's this, oh, I actually had it backwards. The $main class is sort of the synthesized one that shows up. So it's creating an instance of this other class that it generated alongside for us. We see it do the new, do a dupe, do the invoke special to go run the constructor for it. So it's making some other thing out there. All right, then the last big thing that it does, it finally runs that launch. And it hands it a number of different parameters that it's expecting to be on there. At least one of them is that special object that we just newed up is what it's going to pass in. So that's interesting that it's sort of like constructing this other object and then handing it along, when to us at the top level, we didn't see any of that. So what's in that generated class? That's where the magic appears to be happening, that's making this happen. So let's go crack it open. So this class, we're not necessarily going to know any of the method names to look for. We don't have that hint because we didn't write this class ourselves directly. Kotlin wrote it for us. But if we look around, there's a couple of hints, a couple of things that look very interesting. One of them is that there's this invoke method. Like that seems pretty important, right? Run the thing, go invoke the thing, do the work. This invoke does a couple of different loads, calls a few little bits, and then eventually calls into an invoke suspend. And this starts getting to the territory that we were talking about, right? So those suspend functions tell us where we can start and stop. So apparently, somehow this class is involved with how that suspension actually works. Well, let's go take a look at what invoke suspend does for us. It's actually just another method on this same thing. So there is a field. It is not named nicely. They named it I, which is not quite as telling as it could be. But we're going to go load 0. That's load from this, and then get that field value. And so there's a field I that we're looking at, and then we do what's called a table switch. Now, this is kind of like a fancy go-to. So it's like a case where you can match what the value is to the left, the labels, and then that tells you where to go to in this particular method. And so for us, we're going to start, when we start off, this is 0. So we're going to need to go to byte number 40. And the next label that's of interest after that is 63. So it looks like the first bit of action that we want is somewhere between 40 and 63 in this method. So quite a bit of stuff happens here. We can see sort of a throw on failure, a little bit of like coroutine continuation, some built-in stuff. We push and pull things. But on line 53, byte 53, there we finally see some action that looks familiar. This is invoking our first method. So this is where the actual invocation of our suspend function that we asked for. So it's got this wrapping around it, but this is where the coroutine is actually finally going to do the work that we asked it to do as that first step. Now, interestingly, right before it does that, it changes that I field to increment it to the next location. So it puts 1 into that to say, okay, I'm done with doing the first section. Go to the next time that you're called. And so it saves that value, invokes first, and then it just returns back from this invoke suspend. And so what's happened here is the coroutine machinery, it creates an object to track the state of the coroutine as it moves through its life cycle. Each time it decides that it's time for it to execute the next step, it calls invoke suspend. And invoke suspend is just a state machine that keeps track of where it was in the progression and calls the next piece. Kotlin, under the covers, has sort of synthesized this big table, this big method that it can hop around in to keep track of the state, so that what looks like just linear code to us in our Kotlin, at the Kotlin level, can get pieced up and executed at different points in time. So the bytecode reveals to us how Kotlin was able to do this pause and resume. Now, there's a whole bunch of framework code behind it that Kotlin is using to do its own decision about when to execute and when not. But this shows us how it transformed our code into something that can work with that platform code to be able to execute. So that's where we are. To wrap up, we've looked at the tools for digging in, how we can look at bytecode and understand a little bit of what's going on, some of the most important instructions that we've got there. And then we saw what it could teach us about concurrent updates, tail recursion, and coroutines from Kotlin. And so hopefully you can come away with this with a little bit of an extra tool in your tool belt if you didn't have it before. I'll be honest, I don't dig into bytecode every single day. I don't dig into it even every week. But it's a powerful technique to be able to understand what the platform is doing underneath, to be able to see those things that your code, when it gets transformed, when it looks exactly like you thought, and when it looks like something totally different than what you thought you were writing. And those are really valuable things to be able to see and understand how your system's working. So hope that you've enjoyed it. I hope that you'll go disassemble a class that you've got in one of your projects, and I thank you for your attention.